studies. If you have a first-order transition, there's no quantum criticality associated with it. It's really just two different phases crossing in energy. If you go above that finite temperature, there'll be a first-order line coming out. And maybe it goes like this. If we're lucky, it goes in this direction. So when you're above that line, you're actually in the other phase. So then maybe you could actually expect to see something related to Kitaev. At least it's a scenario. About the only one I can think of where you really could expect to see Kitaev physics close. Here I should think about it. Iridates, okay, those are all mostly iridates, those Kitaev things, but not all of them. We had lots of cool talks about iridates. Certainly mostly on the experimental side. They're beautiful experiments, really amazing on strontium iridate, DJ Kim. Now seeing this kind of D-wave gap, which, maybe it's superconductivity. Surely we as theorists, experimentalists can hope to learn something. We as theorists can hope to learn something about high TC from this. Have another system that seems to be behaving the same way. What do we actually learn? Or conversely, can we do our job as theorists and actually predict something that's different here than in ITC? I don't know. Maybe we should just place bets whether it's actually superconducting or not. Of course, those aren't the only iridates. Perhaps a little too close to my heart are these particle iridates. We saw a bunch of very rich experiments doing really complicated things. I think the imaging of domain walls is really beautiful. And we had a couple theory talks, but pretty much all the theory, myself included in there on this, is mean field theory. And yet we know that there are many aspects of the experiment in these materials that are very non-mean field-like. You actually look at this ARPA spectrum that Nakatsuki-san showed us, the bands, to the extent you can even see the bands there are maybe 3 times narrower than they should be, according to DFT type calculations. So that's a big effect. We know there's something pretty majorly wrong about this mean field treatment in that sense. So how much can we trust what it's actually telling us? Mean field theory predicts lots of interesting nodal states, but are they actually there, and can we do better? Since I was told I don't really have to overview, I thought I would now spend the rest of the time telling you about my own theoretical ideas. So I've got about 15 topics we're going to cover, and there's no more talks today, so you can just go, right? So it is Friday, the end of a long week, and you're probably starting to feel like this guy ready to get out of here. I just want to leave you with a kind of quick message, which is, again, sitting here at the KITP, we see programs come through over and over again, covering all the areas of condensed matter physics and other areas. And we've had quite a few interesting ones. And the last few have been, let me say, much more formal than the ones we've had now. And there's a huge community really active and doing exciting things in condensed matter theory who are pushing the boundaries of what we could even call condensed matter theory. I don't know where they come from. Who have invented thousands or millions of new phases of matter, all topological in some way or another, and yet almost no connection to reality. So in this room, and in this program, we've got an impressive collection of people. I'm mainly talking to theorists here, I guess, because you experimentalists are also impressive. I'm supposed to be talking to theorists who maybe have the capability of actually bridging that gap. And talking to, trying to make a connection and talking to these people and to connect the world, the real world, to some of these beautiful ideas. George is one of the guys who might be capable of doing it. He's got a bottle of Georgian wine there, and his favorite number on his shirt. So I just would like to urge you all to try and, one of the things we might manage to do in this program is to build some bridges across the zip line. don't want anyone to leave out. I'm done. I have very little to say, and I've said it. So, like today, I want to just end by thanking all the organizers.
Okay. Ask you all the questions that couldn't be answered during the conference.
Come on. The guy gave a talk, which makes it impossible to ask questions.
Hello. So, looking at the phase,
Apparently not.
looking at the phase diagrams that you showed for the example, you said that if you have a first order transition line, then above that you might expect, if you're lucky, some NI. The question is it the same for 2D versus 3D materials, or is there any dependence on the dimensionality, whether it would be first order or second order?
I'm not predicting whether this transition is first order or second order. I'm saying if it happens to be, then you have this line extending up. But that's general. That doesn't depend on dimensionality. That's just thermodynamics, that a first order transition into a temperature always extends some amount into a finite temperature line. Whether this transition is first order, generally anything can, but universality thinking tells us at least it also depends on the nature of the ordered state over here. So I'm not saying this is the only way. It's just the only way I could think of that might work. I mean, if we want to be really creative, we could probably come up with some other scenario where something might remain. Maybe only part of the degrees of freedom of the spin liquid are involved in the quantum critical point, and some are not really, and those kind of move through. One needs to argue.
Actually, I have a very small comment on that point. Very limited information from calculations. In the anisotropic limit, we did both 2D and 3D calculation for that kind of phase. And we have shown that the 3D case is first order, and 2D case is continuous to decrease. I don't know if it is general or not, but at least in our case, there was a difference.
I think it's model dependent, but that was for this toric code type model, right? Interesting.
Maybe you could tell us your predictions about having a doping of charge carriers in this phase diagram.
My prediction. Well, of course it's going to become superconducting. At very high TC and topological. Wow, okay. It doesn't really matter. If you get it right, you get credit. If you get it wrong, they forget. Yeah.